Hello, saver. Whether you're saving for that trip to the tropics or saving for an emergency, now is the time to take advantage of Wells Fargo's savings options. Wells Fargo offers savings accounts that can help you save towards your goals. So, what are you saving for? Visit a Wells Fargo branch or wellsfargo.com/save to open a savings account today.
Wells Fargo Bank, N.A., member FDIC.
Wells Fargo presents one of the surest ways to grow your money, a Wells Fargo CD account, where you can earn a 5.00% annual percentage yield on an 11-month term with a minimum opening deposit of $5,000. Visit a Wells Fargo branch or wellsfargo.com/CD rates to open a CD account and start growing your savings with us.
Wells Fargo Bank, N.A., member FDIC.
This is SpaceTime Series 24, Episode 127, full broadcast on the 8th of November 2021. Coming up on SpaceTime: discovery of the origins of empty sky gamma rays, understanding the depths of Jupiter's Great Red Spot, and the biggest solar flare so far of the Sun's new cycle. All that and more coming up on SpaceTime.
Welcome to SpaceTime with Stuart Gary.
A new study has confirmed that star-forming galaxies are responsible for generating the majority of so-called empty sky gamma rays, the origins of which have been a mystery for half a century. The findings, reported in the journal Nature, have resolved a long-standing question about some of the most highly energetic forms of light in the universe, which appear in patches of seemingly empty sky. Astronomers have been speculating about the source of empty sky gamma rays ever since their detection in the 1960s. Now, if we leave out matter-antimatter collisions, there are two primary sources which can produce large amounts of gamma rays. One happens when material falls into a supermassive black hole and is ripped apart at the subatomic level. These active supermassive black holes are known as active galactic nuclei because they're found at the centers of galaxies. The other is associated with star formation, and this primarily occurs in the disks of galaxies. So, the authors modeled gamma ray emissions from galaxies and compared their results with predictions for other possible sources. They were able to pinpoint what created these mysterious gamma rays after first obtaining a better understanding of how cosmic rays, particles travelling superluminally, that is close to the speed of light, move through gas between stars. Cosmic rays are important because they create large amounts of gamma ray emissions in star-forming galaxies when they collide with interstellar gas. Data from the Hubble Space Telescope and the Fermi Gamma Ray Space Observatory were key to uncovering the unknown origins of these gamma rays. The authors were able to use data from these sources to analyze information about multiple galaxies, including their star formation rates, their total masses, their physical size, and their distance from Earth. They found that it was star-forming galaxies which were producing the majority of this diffuse gamma radiation rather than active galactic nuclei. The study's lead author, Matt Roth from the Australian National University, says their new model could also be used to make predictions for radio emissions from star-forming galaxies, which could help scientists learn more about the internal structure of these galaxies. He says the new technology will hopefully also allow astronomers to observe many more star-forming galaxies and gamma rays compared to what can be detected now with current gamma ray telescopes. In fact, Roth and colleagues are now looking at producing maps of the gamma ray sky, which could be used for upcoming gamma ray observations using the next generation of telescopes. And these would include the Cherenkov telescope array, which Australia is a part of. Roth says the discovery could also offer clues to help astronomers solve other mysteries in the universe, such as the kinds of particles likely to make up dark matter, one of the holy grails of astrophysics.
Gamma rays are essentially the highest energy form of light we can observe. And turns out if you have your gamma ray telescope up in space and you look at sort of empty patches of the sky, we do see and we do record quite a number of gamma ray photons coming from areas of the sky that don't have an obvious source. So these are essentially just gamma rays that seem to be coming from nowhere because we can't actually make out anything that would be producing them directly. So we've looked at how many gamma rays are produced in star-forming galaxies, of which there are many, many in the universe. And we've basically produced this model and then summed up the total contribution of all star-forming galaxies in the universe and compared that to the measurement of this diffuse gamma ray background. And turns out that we get a really good match to what's being observed.
How did you go about working out that these gamma rays are coming from star-forming galaxies?
The key mechanism that produces these gamma rays in star-forming galaxies is these cosmic rays. So cosmic rays are just particles. So gamma rays are light. Cosmic rays are particles. So they're electrons, protons that are accelerated in supernova explosions. So in the shock waves of the supernova explosions. So when these cosmic rays zip about the galaxy, so we can also measure them in our own galaxy, they zip around, they occasionally bounce into an atom of the gas that sort of fills the galaxy between the stars. And when that happens, they produce another particle called a pion. So they produce three different kinds, but the one that's of interest to us is the neutral pion. So it has no charge. And what happens there is that the pion is very short-lived and it just decays into two gamma rays. So understanding how these cosmic rays move about the galaxy is the critical bit in this.
And the importance of the neutral charge, I take it, is that way it's not influenced by magnetic fields or anything like that.
Yeah, So the neutral pion won't be influenced by anything else. The charged pions, pi plus and the pi minus, they're produced in roughly equal numbers, so there's a third of each approximately. The charged pions decay into electrons and muons and neutrinos and into other particles, which are also very interesting, but it's the neutral pion which is of the biggest interest to us because that produces these really high energy gamma rays in galaxies. So understanding how these cosmic rays move, so how many actually bounce into the gas and how many escape the galaxy, that's work that was also done at ANU, and this sort of fed into the model that we built. So this was the motivation that we understood how they move about and what the gamma ray spectrum of an individual galaxy would look like. And then naturally, the question that poses itself then is, well, if we know how many gamma rays one galaxy produces, what if we apply this to a representative sample of all the galaxies in the universe, and what does that tell us about the gamma ray background? So that was the underlying idea.
When we look at our own galaxy, we see these huge Fermi bubbles emanating from near the galactic center, where we think they're associated with Sagittarius A star, the supermassive, well, what we believe is a supermassive black hole at the center of our galaxy. How do you know that these gamma ray sources are from star birth and not star death?
They are actually from star death. So when we talk about star-forming galaxies and star formation, so the way it works is that you just have some gas that collapses, under gravity and then heats up internally. And then at some point you have enough temperature to start fusing hydrogen into helium and you form a star. So stars above a certain mass, so this is roughly 8 times the mass of the sun, 8 to 9 times the mass of the sun, they actually lead very short lives. So they live a couple of million years and then they die in a supernova explosion.
This is the James Dean syndrome, we call it. Live fast and die young.
Exactly. So the heavier the star, the more quickly it burns its fuel. So they die very young. So when you have a certain star formation going on, at the same time you see a lot of star deaths happening at the same time. So they're very closely related in time. So when we say star-forming galaxy, that means that we have a lot of stars dying at the same time as well. So you need the supernova explosion to produce the shock waves to accelerate the cosmic rays. So that's the critical bit. So the two mechanisms are very closely related in that sense.
Because of the characteristics of gamma rays and how they radiate, I guess is the word I'm looking for, does this provide any clues at all into things like dark
matter is of particular interest because some of the dark matter theories have particles which they're called WIMPs, so they're weakly interacting massive particles. And basically the rundown is that they're fairly heavy particles. So we would assume that they have some probability of annihilating either with the antiparticle or with themselves. So if we look at of areas where we would expect the dark matter density to be relatively high. So this is, for example, at the center of galaxy clusters, or even just at the center of a galaxy. You can think about a scenario where you have dark matter annihilation, and because these particles are very heavy, you would expect that radiation to be coming out in gamma rays. So one of the key things for looking for such a signal is that we need to be able to model backgrounds. So we need to know what all the other gamma ray emission is that might be in that area, to subtract it from what we see, and then whatever signal you're left with, that is then the one that may yield some clue as to what dark matter may be. So these experiments are, ongoing, and if you go through the literature, there's always a lot of discussion going on whether some things may be hinting at a signal or not. So this is a big field of research, and it's red hot essentially.
I guess the other important thing here is that you didn't find any huge areas of the universe full of gamma rays. So I guess that means the whole universe is a matter universe, not half matter, half antimatter.
So we've known that for a good while, because otherwise we'd be in big trouble.
Yeah, but you hope, you hope there's maybe half a universe out there that's all antimatter, and that way the equations all work out. Yes.
Where has all the antimatter gone? That's right. Yeah, you wouldn't have to explain that problem then. That we have it's significantly more matter than antimatter in the early universe. There's still lots of different little problems in different areas of physics. So there's still lots more to discover, and you always build on a lot of work that other people have done before. So what we've done relied on significant work from other people, to come up with these surveys, to give us sort of the input parameters into our model. So it's a step-by-step process. So, as they say, standing on the shoulders of giants is a big theme here, really.
That's Dr. Matt Roth from the Australian National University. And this is SpaceTime. Still to come, understanding the depths of Jupiter's Great Red Spot, and the Sun's new solar cycle off with a bang with the biggest solar flare so far. All that and more still to come on SpaceTime.
Hello, saver. Whether you're saving for that trip to the tropics or saving for an emergency, now is the time to take advantage of Wells Fargo's savings options. Wells Fargo offers savings accounts that can help you save towards your goals. So, what are you saving for? Visit a Wells Fargo branch or wellsfargo.com/save to open a savings account today.
Wells Fargo Bank, N.A., member FDIC.
New data from NASA's Juno spacecraft shows that Jupiter's iconic Great Red Spot extends downwards some 500 kilometres below the cloud tops, far deeper into the gas giant than previously thought. The Great Red Spot is Jupiter's most iconic feature. The 16,000-kilometre wide anticyclone has been churning in the planet's atmosphere for centuries. The new findings, covered in several research papers reported in the journals Science, Geophysical Research Planets, and Geophysical Research Letters, are revealing new insights into the Jovian cloud structure, its meteorology, and the planet's deeper interior. Juno achieved Jupiter orbit insertion in 2016. During each of the spacecraft's 37 highly elongated orbits around the gas giant, a suite of instruments peered deep down through the planet's turbulent cloud tops as the probe swoops over the clouds at some 209,000 kilometres per hour, so as to spend as little time as possible in Jupiter's intense radiation belts. Gigantic storms and bands of rotating winds abound in Jupiter's atmosphere, including, of course, the Great Red Spot, a storm so massive it could easily swallow the Earth whole. However, it's unclear whether these storms are confined to just the uppermost parts of the planet's atmosphere or whether they extend deep into the Jovian interior. So scientists have been using microwave and gravity measurements from Juno to characterize Jupiter's atmospheric vortices, including the Great Red Spot. Juno's microwave radiometer studied the vertical structure of the Crimson Vortex. During its latest flyby, Juno's microwave radiometer studied the vertical structure of the Crimson Vortex as well as two other giant storms, finding they extended far below the planet's cloud base, the altitude at which water and ammonia are expected to condense. This is especially interesting for the Great Red Spot, as it suggests the presence of small-scale dynamic processes such as precipitation and downdrafts at much deeper levels than previously expected, which may indicate a connection between Jupiter's interior and deep atmosphere. Juno also grabbed a gravity signature from the massive tempest during its latest flyby. It showed fluctuations in the planet's gravitational field caused by the storm. Although the Great Red Spot stretches more than 500 kilometres down through the Jovian atmosphere, it's far shallower than the surrounding zonal jets which power it. Principal investigator Scott Bolton from the Southwest Research Institute in San Antonio, Texas, says earlier Juno data showed that Jupiter's atmosphere reached deeper than thought, and the new data shows that extends up to 3,000 kilometres deep. Bolton says the new data helps put the earlier pieces together, revealing a beautiful and violent atmosphere. The new results show that the Jovian cyclones are warmer at the top, with lower atmospheric densities, and cooler below, where there are higher densities. At the same time, anticyclones like the Great Red Spot, which rotate in the opposite direction, are colder at the top, but warmer at the bottom. Of course, in addition to cyclones and anticyclones, Jupiter's also known for its distinctive belts and zones, white, reddish and salmon-coloured bands of clouds that wrap around the planet. Strong east-west winds moving in opposite directions separate these bands. These winds or jet streams reach depths of around 3,200 kilometres, and scientists are still trying to solve the mystery of how they're formed. Data collected by Juno during multiple passes reveals one possible clue. It turns out the atmosphere's ammonia gases travel up and down in remarkable alignment with the observed jet streams. By following the ammonia, scientists found circulation cells in both the northern and southern hemispheres, which are very similar in nature to Forel cells, which control much of the Earth's climate. One of the study's lead authors, Karen Dua from Israel's Weizmann Institute of Science, says while Earth has one Forel cell per hemisphere, Jupiter has 8, each at least 30 times larger. Juno's data also shows that these belts and zones undergo a transition around 65 kilometres beneath Jupiter's water clouds. At shallow depths, Jupiter's belts are brighter in microwave light than neighbouring zones. But at deeper depths, below the water clouds, the opposite's true. And that reveals a similarity with Earth's oceans, where seawater transitions sharply from being relatively warm to relatively cold at a point known as the thermocline. This is SpaceTime. Still to come, the biggest solar flare in the Sun's new solar cycle, and later in the science report, forget Christopher Columbus, we now have confirmation that Vikings crossed the Atlantic Ocean a millennia ago. All that and more still to come on SpaceTime. The Sun has launched its second X-class solar flare of the new solar cycle, leaving no doubt that solar cycle 25 is underway. Solar flares are explosions of energy caused by the sudden snapping of tangled and twisted magnetic field lines called flux ropes, which emanate from sunspots on the solar surface. Sunspots are cooler regions on the Sun's surface that appear darker than surrounding areas because the magnetic field lines reaching out into space from deep inside the Sun prevent some of the heat from within the Sun from reaching the surface. Different latitudes of the Sun rotate at different rates, causing these field lines to become tangled and twisted, eventually snapping and realigning through magnetic reconnection, in the process producing an eruption of electromagnetic energy called a solar flare, which if facing the Earth will reach the planet in less than 8.3 minutes, the speed of light. X-class solar flares like this one are the most intense. The new flare was classified as an X1, the number providing information on the strength of the flare. So an X2 is twice as intense as an X1, and an X3 is 3 times as intense. Flares that are classified X10 or stronger are considered unusually intense. The new flare, which erupted in time for Halloween, followed a series of smaller flares which all erupted from the same active region on the left limb of the Sun. These included a coronal mass ejection and an invisible swarm of solar energetic particles. Then a far more active region in the Sun's lower centre released the big X1 class flare from sunspot AR2887. The blast created a massive tsunami of plasma in the Sun's atmosphere, which rippled right across the entire solar disk. It was followed by a halo coronal mass ejection, which hit the Earth on November the 4th and 5th. Solar cycle 25 began in December 2019. A new solar cycle comes roughly every 11 years. Over the course of each cycle, the Sun transitions from relatively calm to active and stormy, and then goes quiet again. At its peak, known as solar maximum or solar max, the Sun's magnetic poles flip. The Sun's positive pole becomes negative, and its negative pole becomes positive. If solar flares are powerful enough, they'll also eject billions of tons of coronal plasma and embedded magnetic field, frozen in flux, from the Sun's corona, exploding out from the Sun at speeds of 3,000 kilometres per second, which, if facing the Earth, will reach our planet in just 15 to 18 hours. When these geomagnetic storms reach the Earth, the flux of ionized particles slam into our planet's magnetosphere, and they're then guided by the planet's magnetic field lines through the ionosphere, region already filled with charged particles, towards the Earth's north and south magnetic poles. As these charged streams of plasma travel through the Earth's upper atmosphere, they collide with oxygen and nitrogen atoms and molecules, causing them to excite and emit photons, giving off a glow and producing colourful curtain-like displays known as the Northern and Southern Lights, the Aurora Borealis and Aurora Australis. The colours being emitted depend on the particles being ionised. Reddish-brown glows are caused by the collision of particles with single oxygen atoms in the Earth's upper atmosphere, usually above 300 kilometres. Lower down, a green hue is created by single oxygen atoms down to altitudes of about 100 kilometres. The kaleidoscope turns a whitish yellow beige when nitrogen's mixed in with the oxygen. Aurorae can also exhibit blue, red or even purple glow in the lower atmosphere, caused by the excitation of molecular nitrogen below 100 kilometres. However, as well as the spectacular auroral light shows, these highly charged particles can also damage or even destroy spacecraft by shorting out their electronics and destroying circuits. They also cause the atmosphere to physically expand and contract, increasing atmospheric drag on orbiting spacecraft, resulting in premature orbital decay and the need to use up more fuel in order to maintain an operational orbit. Worse still, space weather increases the level of radiation exposure astronauts experience. That'll affect their health. On the ground, these solar storms can overload power lines, causing widespread blackouts. In fact, in 1989, one of these geomagnetic storms blew out transformers, causing massive blackouts across most of eastern North America. Space weather also affects communication and navigation systems, and it forces polar airline flights to be rerouted using up more fuel. This is SpaceTime.
Wells Fargo presents one of the surest ways to grow your money. A Wells Fargo CD account, where you can earn a 5.00% annual percentage yield on an 11-month term with a minimum opening deposit of $5,000. Visit a Wells Fargo branch or wellsfargo.com/CD rates to open a CD account and start growing your savings with us.
Wells Fargo Bank, N.A., member FDIC.
And time now to take a brief look at some of the other stories making news in science this week with a Science Report. Australians and Americans are now following in the steps of Israel and getting a third booster shot of the COVID-19 vaccine. A report in the Lancet Medical Journal supported the third dose option, saying results from one of the world's largest integrated health record databases show that compared to individuals who received only 2 doses of the vaccine 5 months prior, individuals who received 3 doses of the vaccine had a 93% lower risk of COVID-19 related hospitalization, a 92% lower risk of severe COVID-19 disease, and an 81% lower risk of COVID-19 related death. Vaccine effectiveness was found to be similar for different ages, sexes, and the number of comorbidities. The findings come as many countries begin experiencing a resurgence of SARS-CoV-2 infections despite successful vaccination campaigns. More than 5 million people have now been killed by the COVID-19 coronavirus ever since the deadly pandemic first spread out of Wuhan, China. However, the World Health Organization believes the real death toll is likely to be twice that level, with well over 250 million people now infected. Well, you can forget Christopher Columbus. Archaeologists have found evidence that Vikings were present in Canada 1,000 years ago, confirming them as the first Europeans to cross the Atlantic Ocean. The findings, reported in the journal Nature, are based on a tree ring analysis of 3 wooden items found in an ancient Norse settlement in Newfoundland. The location appears to have been a base camp used by Vikings to explore other parts of North America. The 3 pieces of wood came from 3 different trees. All were from context archaeologically attributable to the Vikings, and each displayed clear evidence of cutting and slicing by metal blades, a material not produced by the indigenous population of the period. The exact year was determined because of a massive solar storm which occurred in the year 992. This produced distinct radiocarbon signals in tree rings, and there were 29 yearly growth rings after this signature, meaning the trees were cut down in the year 1021. That's exactly 1,000 years ago. A new study shows that Australia has the world's second highest rate of methamphetamine use. The findings by the Australian Criminal Intelligence Commission looked at 24 countries on 4 continents, finding only Slovakia had a worse record than Australia. Methamphetamine exists in 2 forms, a powder known as speed and crystal methamphetamine, commonly known as crystal meth or ice. The study found that alcohol and nicotine remained the top drugs of choice for Australians, while methamphetamine was the most popular illicit drug, with high use in both rural and urban areas. The report found declines in the use of MDMA, cocaine, heroin, fentanyl, and oxycodone, although that could be due to COVID-19 pandemic-related declines in festivals and open entertainment venues, along with decreased imports of illicit drugs. Health problems linked to amphetamine use include suicide psychosis and anxiety, an increased risk of sexually transmitted diseases through uninhibited sexual behaviour, and a range of cardiovascular disorders, including heart conditions and sometimes stroke at a very young age. Have you ever noticed how many evil villains have PhDs? There's Dr. Doom, Dr. Octopus, Professor Moriarty, Dr. Death, Dr. Hannibal Lecter, and of course, Dr. Jekyll's Mr. Hyde. And it's not just in the world of fiction. Every disreputable cause seems to have a pet scientist, willing to roll over and have their tummy rubbed for the right price. Now, a new study reported in the Journal of Experimental Social Psychology shows that this tactic works, and it's a good way to dupe people who trust science into believing in pseudoscience as well. Tim Mendham from Australian Skeptics says that's because things that sound sciencey usually give the impression of actually being science when they're not.
Once upon a time, the teaching of pseudoscience was pretty blatantly weird, and people promoting all sorts of strange things didn't really go into very sort of scientific terms. There was a lot of just mumbo-jumbo. Over the years, they've improved what they wrap their theory in to sound more sciencey, to use more terms, etc., that would make them sound more impressive. Now, the problem is, if science is being taught as, don't worry about not understanding it, trust me, it's science, that means people are less able to discern between pseudoscience and science. And therefore, like in many of the things we're talking about here, in the pandemic at the moment, you just say, trust the experts. And that is the key thing, that people promoting pseudosciences and anti-vaxxers and that sort of people are hitting on 2 fronts. They're saying, you can't trust experts, except you trust my experts. The irony of that is that they put forward a scientist or a pet scientist or whatever to promote their particular claims. And then you say, everyone else you don't trust because they're scientists and therefore compromised. So people who are told to trust science without going into great understanding of what the scientists are doing are prone to actually believing in all sorts of strange things because they don't discern between trusting a scientist and trusting a pseudoscientist, and they're not taught to.
The best example of that is the well-known geologist who is constantly being touted as an expert on climate change.
Yes, Yes, I mean, he's a scientist, but he might not be in the best area. But the interesting thing is that a lot of people who deny climate change keep putting forward a particular survey that was done, which they point out 30,000 people who are climate science experts. And you look at this list and say, no, they're not. They come from every different area you can think of. I mean, doctors. I don't know how many doctors are actually experts on climate change. I don't know how many Spice Girls are experts on climate change. Ginger Spice was actually one of the people on the list. I think Mickey Mouse was as well. But that's a bit unfair. Okay, not that many out of the 30,000, but the vast majority of the 30,000 were not experts in climate change. So be careful of the list quoting 30,000 people. It's not 30,000 relevant people. And you're getting people in certain areas, geologists who work in super millennia, sort of eons of time frames, trying to equate what they see as the change of climate on a geological level to what's happening now in climate change on an environmental level, which is a lot shorter and a lot more concerning. But so just trusting a scientist is a problem area, but we aren't qualified, most of us, to actually understand the science.
And if you talk enough scientific jargon, people automatically believe it. I was listening to a guy, what he was saying was total gobbledygook. It made no scientific sense at all. But unless you actually understand the science, what he said sounded perfectly logical, but it wasn't science, it was garbage.
Yeah. That's why you see a sort of naturopath wearing a white coat and carrying a stethoscope. They basically know what they're talking about, but they don't. They're just putting on a white coat. And it annoys me all the time when you see pictures of doctors always wearing white coats and carrying stethoscopes around us and see, I'm an authority. And other people can pick up the same thing and use it and misuse it and convince people where it's wrong to do so. But, the people themselves are part of the problem. The believers are part of the problem, or the general public. If you're just told to believe science, which sometimes you have to do because the science is pretty complicated, it leaves you vulnerable.
That's where the education comes in. You've got to be able to discern that difference, which is really tough sometimes if you're not an expert with years of experience in that field anyway.
It is. It's very tough. But if you have to, you can look for the signs of pseudoscience, and the way that it's presented and the manner of the people presenting it. And that's the secret. You might not understand all the science and the real science and be able to differentiate that from the pseudoscience, but if you understand the way a story is being presented, you might sort of then get a different opinion. Simple one, if someone says this is 100% true, it's pseudoscience for a start. No scientist will say this is 100% true.
And that's one of the problems because there is no absolutes in science. So
I would say it's 99.9999% sure that the sun will rise tomorrow, but you never know, right? Apart from the fact that it doesn't rise, we turn. I know that, blood. That's being picky. But the sun will come up over the horizon tomorrow. It's pretty well certain, and so anyone who says 100% correct, I can do this 100% of the time, I can cure cases 100% of the time, instantly it's a pseudoscientist. So that's one test you can use if you're trying to discern between a real scientist and a pseudoscientist.
That's Tim Mendham from Australian Skeptics. And that's the show for now. SpaceTime is available every Monday, Wednesday and Friday through Apple Podcasts, iTunes, Stitcher, Google Podcast, Pocket Casts, Spotify, Acast, Amazon Music, Bytes.com, SoundCloud, YouTube, your favourite podcast download provider, and from spacetimewithstuartgary.com. SpaceTime's also broadcast through the National Science Foundation on Science Zone Radio and on both iHeartRadio and TuneIn Radio. And you can help to support our show by visiting the SpaceTime store for a range of promotional merchandising goodies, or by becoming a SpaceTime patron, which gives you access to triple-episode commercial-free versions of the show, as well as lots of bonus audio content which doesn't go to air, access to our exclusive Facebook group, and other rewards. Just go to spacetimewithstuartgary.com for full details. And if you want more SpaceTime, please check out our blog, where you'll find all the stuff we couldn't fit in the show, as well as heaps of images, news stories, loads of videos, and things on the web I find interesting or amusing. Just go to spacetimewithstuartgary.tumblr.com. That's all one word, and that's Tumblr without the E. You can also follow us through @StuartGary on Twitter, @SpaceTimeWithStuartGary on Instagram, through our SpaceTime YouTube channel, and on Facebook, just go to facebook.com/SpaceTime with Stuart Gary. And SpaceTime is brought to you in collaboration with Australian Sky and Telescope magazine, your window on the universe.
You've been listening to SpaceTime with Stuart Gary. This has been another quality podcast production from Bytes.com.
Wells Fargo presents one of the surest ways to grow your money. A Wells Fargo CD account, where you can earn a 5.00% annual percentage yield on an 11-month term with a minimum opening deposit of $5,000. Visit a Wells Fargo branch or wellsfargo.com/CD rates to open a CD account and start growing your savings with us.
Wells Fargo Bank, N.A., member FDIC.